Good afternoon. We are going to be taking notes on 5.5 rational numbers as exponents. Now, we've been using radicals for a great many things, but I want to start by showing you how this new material is going to help us accomplish things that we couldn't in radical form. So here we have the cube root of 2 times the square root of 2. So there's an invisible 2 there. Now, in radical form, root 3 is not equal to root 2, and so it would be not possible to multiply these together. However, because they both have a base of 2, we can use exponential notation to do the math. So the math isn't going to make sense yet, but the process results will. So this is 2 to the power of 1/3. This is 2 to the power of 1/2. So keep the base, add the exponents, 1/3 plus 1/2. Of course, we're going to need a common denominator. So 2/6 plus 3/6 is 2 to the 5/6. And then this gets converted back to radical form, 2 to the 5th with a 6th root. And then, of course, we would simplify. So we put the radicals into exponent form so that we could multiply them, and then we put them back into radical form when we're done. So that's the primary use of radical to exponential form, is for combinations such as multiplication and division. All right, so let's start the main notes. Roman numeral 1, we're going to learn theorem 7-6. So draw yourself a radical with an a in the radicand to the power of m. The radical is an index of k. What this property lets you do is move that exponent out of the radical. So we're going to have a still on the inside with a root k, but the m moves to the outside. This only works if a is a monomial. It does not work for very many other things. All right, nice thing also, this is biconditional. It works forwards and it works reverse. You will use it when it makes your life easier. Okay, so on your worksheet, one of the first questions is to simplify, and then it says do it again, but you're going to simplify using theorem 7-6. So I'm going to give you an example of that you can follow like a pattern. Okay, so the first way you're going to do it is the old way we've been simplifying, which is from the inside out. So we're going to use the cube root of 64. Now, the old way of doing this would be to prime factor 64, which is 8 times 8. So 222 for the first 8, 222 for the second 8. Then we would, because this is a cube root, we would count 1, 2, 3 2s. One comes out. 1, 2, 3 2s. Another one comes out. No more radical. 2 times 2 is 4. That is the first method. Okay, so the second method, this is the new one, which is theorem 7.6. And to use this method, we're going to move the exponent out of the radical. Move the exponent out of the radical. So here we go again, cube root of 64. Now you'll notice we don't have an exponent. So what we're going to do is rewrite 64 as 8 squared. Now that we have an exponent, we're going to move it out. So I have the cube root of 8 quantity squared. So now what we can do is treat the cube root of 8, which is a much smaller, simpler number, and only do that one time and then multiply it by itself. So cube root of 8, 8 is 2 times 2 times 2, 3 2s, 1 comes out, nothing's left. Since I have another cube root of 8, this one is going to also end up with a 2. We multiply and get 4. So we get to the same answer just using a different approach. All right, so when is it okay to use theorem 7.6? So I want you to draw a little box out here. We're going to go through some examples of things you can use it for and things you can't use it for. Okay, so the first one on the list is the cube root of 3 squared x. Now in this one, the x is not being squared, just the 3. So this is a no, we cannot use 7, 6. Now, if it's the cube root of 3x quantity squared, now that the whole radicand is to the power of 2, yes, we can use 7.6. Okay, what about the cube root of 3 squared plus x? Well, 3 squared plus x is a binomial, and this only works with monomials. So this is a no because it is a binomial. Now, here's an example of a binomial in parentheses, 3 plus x quantity squared. Because it's the entire radicand to the power of 2, yes, we can use 7.6 because this binomial is acting like a monomial. And the last one, cube root of 3 squared plus x squared. Even though they're both raised to the power of 2, they are in a binomial form, so that is no. So the two qualities that have to be met for this theorem is the radicand must be a monomial, one term, and the entire radicand has the same power. So it has to be a monomial, and the whole radicand, the monomial, must be to the same power. Then we can use the new theorem. All right, turning the page, we're going to go to Roman numeral 2, which is switching forms. Switching forms. Okay, so first thing we're going to do is change to exponential form. Change to exponential form. And I'm going to use colors to try to make this a little bit easier to understand. So we've got the square root of a. Okay, this is radical form. Now a is to the power of 1. And because it's a square root, there's an invisible 2. So when you change it to exponential form, you keep the same base, base a. The power on the a goes on the top of the fraction. The root of the radical goes on the bottom, so it's a to the power of 1/2. 1 for the power, 2 for the index. Okay, let's do another one. Let's say you've got a squared, and it's in a cube root, so there's our 2. So keep the same base a. On the top of the fraction is the power, which is 2. On the bottom of the fraction, it's the index, which is 3. So a to the power of 2/3. All right, let's do a fourth root. So fourth root of a squared. So it's going to be a base a. On the top of the fraction is a 2 for the power. On the bottom of the fraction is a 4. Now, 2 over 4 reduces. So if your exponential form has a fraction that's reducible, you need to reduce it. So a to the 1/2 would be your answer. All right, last one of these, the square root of 2ab. Now, at first glance, you say, hey, it doesn't have a power, but I can write this as 2ab quantity to the power of 1. So they're all to the power of 1. So to write this in exponential form, keep the same base, 2ab. On the top of the fraction goes the power, 1. And then this is a square root, so invisible 2 goes on the bottom of the fraction. So 2ab to the power of 1/2. Again, the interior must be a monomial, and the radicand, the entire radicand, is to the same power. Otherwise, this algorithm won't work. All right, so let me give you some practice. This is B, so practice. Again, switch the video off and do this on your own and then turn it back on. I want you to convert the cube root of 5. I want you to convert the cube root of 7 squared. And then I want you to see if you can do this one. 2 and then the 4th root of 10. Use a pencil so you can erase. You can turn off the video now and give it a shot. Okay, let's see how you did. This is 5. The power on 5 is 1, so 1 goes on the top of the fraction. The root is 3, so 1/3. Okay, for number 2, I have a base 7. The power goes on top, so 2 on top. Root 3 goes on the bottom, so 2/3. Now the last one, the 2 is not part of the radical, so you're just going to go 2 times, make it a scalar, and then base 10. 10 is to the power of 1, and the index is 4. So 2 times 10 to the 1/4. That way the 2 isn't being raised to the power of 1/4. Okay, part C. Now we're going to change to radical form. So we're going to go backwards. And I think you'll find this is pretty simple. So I'm going to give you the first 2 to do on your own, and then we'll do the third one together. So number 1 is a to the power of m over n. Number 2 is 9 to the power of 2 over 3. So pause the camera and give these a shot before turning the camera on. All right, let's see how you did. So the same base goes inside the radical. The top node is the power, so a to the power of m. The bottom node is the index, so the index or root is n. All right, let's do the next one. Draw your radical, base 9. The power is the top number, so 9 squared. The root is the bottom number, which is 3. Now, this one needs to be simplified because we know that 9 consists of 3. So if I have a 9 squared, I get 3 times 3 for the first 9, 3 times 3 for the second 9. It's a cube root, so 3 3s, 1 comes out, and there's 1 left inside. So sometimes when you are done simplifying in exponential form and you go back to radical form, you will have to simplify the radical. So be watching for that. All right, number 3 we're going to do together. Now this one has a power of -2/5. To do what we've been doing, you can have no negative exponents. So right now we can't convert this number. However, if we move the 32 to the bottom of the fraction, then the 2/5 becomes positive. Now, when you have a radical in the bottom of a fraction, it is irrational and needs to be rationalized. Just because this is in exponential form does not make it rational. So to have this in the bottom makes the expression irrational because you can have no radicals on the bottom. So you're going to have to train yourself to spot radicals on the bottom. All right, so we're going to need to rationalize this, but first we need to convert it back to radical form. So 1 over 32 squared under a 5th root. And as you can see, we really do have a radical in the bottom. Okay, so 32 is 8 times 4, so 2, 2, 2 for the 8, 2 and 2. I'm going to use property 7, 6 and move the squared symbol to the outside. So I have 1, 2, 3, 4, 5 2's. 1 comes out, so I have 1 over 2 squared, which is 1/4. So when I finished simplifying the radical, I actually didn't have to rationalize. If you do have to rationalize, you have to convert back to radicals. Convert back to radicals. In that form, fix it, and we already know how to rationalize. And then if you started in exponential form, you must end in exponential form. So you'll go back to exponential form to end the problem. So you convert to a radical, rationalize it, and then go back again. All right, flip the page. We're going to do 2 more examples of this. All right, so let's do example 4. This will be just like our beginning example, only now you understand it. 4th root of 3 times the square root of 3. All right, this is a 4th root, this is a square root. The indexes don't match, so we're going to flip it to exponential form. So both of these 3's are to the power of 1. So 3 to the 1/4 times 3 to the 1/2. And then remember your exponent property. A to the m times a to the n is a to the m plus n. So it's going to be 3 to the 1/4 plus 1/2. Get a common denominator for your fractions, and it ends up being 3 to the 3/4. Now we switch it back to radical form, so we have a 3 cubed under a 4th root. Obviously, I only have 3 3's, so nothing is going to come back, but I do need to get rid of the exponent. I get the 4th root of 27. 4th root of 27. Okay, so just to reiterate, if the roots are not equal, change to exponential form. If the roots are not equal, change to exponential form and combine terms. Then go back to radicals. So you only go to exponents long enough to do the multiplication, and then you go back. All right, this is the last problem. It's kind of complicated, but I wanted to go through at least one with you. I have the cube root of 5 over the 4th root of 25. So right away, you know you have a problem with the roots. We can't even rationalize in this form unless the roots match. So change it to exponential form. 5 to the 1/3 over 25 to the 1/4. Now you might think that you're stuck because in order to combine these, the roots must match. But we can do a little bit of number changing with your 25 to the 1/4. This is a base 5, so if I can express this as a base 5, I can divide the exponents. So 25 is 5 squared. It's being raised to the power of 1/4. So power to a power rule, this is 5 to the 2/4 or 5 to the 1/2. So I now have this in terms of a base 5. So I have 5 to the 1/3 over 5 to the 1/2. Your division property of exponents is a to the m divided by a to the n is a to the m minus n all over 1, top minus bottom. So using this, I'm going to have 5 to the 1/3 minus 1/2. I need a common denominator, so this is 5 to the 2/6 minus 3/6, which gives me 5 to the negative 1/6. All right, flip that to the bottom because we can't convert with a negative exponent. 1 over 5 to the 1/6, and go back to radical form. 1 over the 6th root of 5. All right, so we've got this thing simplified. Let me put in these equal signs here. But we have a radical in the bottom of a fraction, so we need to rationalize. Now we're already in radical form, so we can work with what we have. I have 1 over the 6th root of 5. To get rid of the radical, I need a total of 6 5s. So I'm going to multiply by the 6th root of 1, 2, 3, 4, 5 5s, which means I have to multiply the top by the 6th root of 5 5s. On the bottom, I'm going to have 6 5s. 1 is going to come out. On the top, I have the 6th root of 5 to the 5th. So not enough 5s to come out on the top. Run that through a calculator. You end up with the 6th root of 3,125 all over 5. So once you get down to your answer, if you need to rationalize, keep it in radical form and do the rationalizing. All right, that is it for today. Have a good afternoon.